Hey, what's going on, MathCounts? So this is just a little bit of deliciousness that I've cooked up to go along with the simplifying radicals stretch from the 2026 problem set. So here we go. So you might have done simplifying radicals before. Remember, when you simplify radicals, it just means that you have to take out any perfect squares, if it's a square root, or cubes that is a cube root, out of the radical. So any factors that are perfect squares. I didn't even write. So take all factors that are perfect squares. So for instance, root 12 is not simplified. It's not simplified because it has a factor inside of it that's a perfect square. So we all know that this is root 4 and root 3. So we have a perfect square in, oh gosh, I got the hiccups. We got a perfect square inside of 12. So this is 2 and then times root 3. And now it's in simplified form. Just a second, I gotta pause and get something to drink because I'm gonna hiccup this whole time. I think I gotta hold myself now. All right. So that's one way to do it, is if you know the perfect square inside of there, you can do that. So for some of my other classes, what I might do is I go, okay, let's do the prime factorization of 12. This is for like if you can't think of the perfect square inside of there. So the prime factorization of 12 would be 2 times 2 times 3. And these two factors right here make this 2 that's out here, because these two factors represent the number 4. 2 times 2 is 4. So if you can find a pair of them, you can take them outside. And then if you have anything left behind, you can leave it inside the radical. Now for the next one, we've got 54 inside of the cube root. So instead of looking for a perfect square, I'm going to be looking for a perfect cube in order to take out. And you might know that the perfect cube for this one would end up being 27. So 27 is the perfect cube of 3. So we could say that this is 3 times the third root of 2. So I broke it up into the perfect cube. 27 times 2 is 54. Now again, if you didn't know that, you could just do something like this. 2 and 27. 27 is 3 and 9. 9 is 3 and 3. But now since the index number up here is 3, we're looking for 3 of a kind, because that would make a cube. So the 3 goes outside and the 2 stays inside the root because it was not a perfect cube. Now, if you have a coefficient that's already out there, so for this one, you might go, oh, this is 6 times root 25 times root 3, because 3 times 25 is 75, and 5 is a perfect square. So you could just do, oh, this is 6 times 5 times root 3, and so your final answer would just be 30 root 3. So if you have a coefficient already, remember everything here is a factor. So if you take a perfect square and turn it into 5, you still have to multiply by the 6 out there because this was a factor to begin with, something multiplied. Again, you could have just split it up. You could have said, oh, I think this is 5 and 15, and it is. And 15 is 5 and 3. So you still have that pair of 5s because it's a square root and not a cube root. So you got that pair of 5s, that's where this 5 comes from right here. And you've got this 3 left over. I'd say 30. So that's where that one came from right there. All right, adding and subtracting radical expressions. So when you add or subtract radicals, you can only add or subtract like terms, which is like the same with everything else too. But when you are having radicals, Like terms are when they have the exact same root. So this one is root 2, and this one is 5 root 2. So since the roots are the same, then we can combine those because they are like terms. We just have to remember that there's nothing out front. We have 1 root 2. So 1 root 2 minus 5 root 2s would be negative 4 root 2s. Over here, these are not like terms because the roots are not the same. But what we can do is simplify them first, and then we'll find out that yes, they do have the exact same root. So for this one, 3 root 8 can be turned into 3 times root 4 times root 2. And then root 4 is 2. So we get 6 root 2. So root 8 became root 4 times root 2. Root 4 became 2. 3 times 2 is 6. We get 6 root 2. We do the same process with the next one. This is 16 times 2. So the square root of 16, that's my perfect square inside of 32. That would be 4 root 2. And now we've got 6 root 2s, and I'm adding 4 root 2s to it, so that means I have 10 root 2s. All right, next. Rationalizing denominators. So one of the rules for radicals and simplifying them is you're not allowed to end your problem with a radical in the denominator. So in order to get the radical out of the denominator, we do something called rationalizing. All it is, in essence, is multiplying by the number 1, which we can do because the multiplicative identity says that I can multiply by 1. But we multiply 1 in an interesting way. We multiply by root 3 over root 3. That's still 1, so I'm using the multiplicative identity, multiplying by 1 and keeping the same number. In the numerator, 6 times root 3 is 6 root 3. And root 3 times root 3 is root 9, or just 3. So anytime I multiply a radical by itself, the radical just goes away. Because basically what I'm doing is squaring here. And squaring is the opposite operation of square rooting. So if I square a square root, the root just goes away. Now I can still simplify. The 3 can reduce with the 6. It can't reduce with the radical though. So our final answer, 6 and 3 reduce, I would get 2 root 3. Over here, I have a radical in the denominator. That's a no-no. So I multiply by root 5 in the numerator and the denominator. In essence, I'm just multiplying by the number 1, and that's fine to do. Radicals multiply with other radicals. So here I would get 2 root 30. 30 does not have any perfect squares in it, so we're good to go. In the denominator, root 5 times root 5 is 5. So this is going to become 3 times 5, because root 5 times root 5 is 5, so my denominator is 15. Again, the 15 cannot reduce with the radical. It could only reduce with the 2, and since it doesn't reduce, we would be done at that point. Binomials and conjugates. So the conjugate of a plus root b is a minus root b. That was really written poorly. A minus root b. When you multiply conjugates, the result is going to be rational, meaning that the radical is going to go away. So here I've got 2 conjugates, 3 plus root 2 and 3 minus root 2. Now I'm going to use an area model just to show what happens here. So I'm basically distributing. The 3 has to be multiplied by these 2. The root 2 has to be multiplied by these 2. All right, 3 times 3, it's 9. 3 times root 2, it's 3 root 2. 3 times negative root 2 would be negative 3 root 2. And then root 2 times root 2 is 2, and there's a negative here, so that would be negative 2. And what I notice is the diagonal here, the 3 root 2 and the negative 3 root 2, have canceled each other out. all I'm left with is 9 minus 2, which is 7. So when you multiply one of these irrational number binomials here, where we've got a rational number and an irrational number, if we multiply by its conjugate, this diagonal is always going to cancel out. This is called the difference of two squares if you've done factoring before. So these cancel out here, and all you're left with is 3 squared minus root 2 squared. All right, last thing. Now we're going to use conjugates to rationalize the denominator. Again, we're not allowed to have radicals in the denominator, but I can't just multiply by root 2. If I multiplied this by root 2, I'd get 2 times root 2 minus 2, right? Because I'd have to distribute the root 2 to both these, and I'd still have a radical down there. So if you have a binomial, you can't just multiply by root 2. You have to multiply by the conjugate, which would be 2 plus root 2. Okay, let's multiply the top. 5 times 2 is 10. We're distributing. 5 times positive root 2 would be plus 5 root 2. In the denominator, 2 times 2 is 4. Negative root 2 times positive root 2 would be negative 2. So in the denominator, we would have 2, and now we have rationalized the denominator. If that confused you what we did right there, just remember that if you do an area model, you can see what's happening with our numbers. Two times 2 is 4. 2 times negative root 2 is negative 2 root 2. 2 times positive root 2 is 2 root 2. And root 2 times root 2 is 2, and then it's negative, so negative 2. So these canceled out, and I'm left with 4 minus 2, which is 2. Last one. So this one, I've got a binomial down here, so I'm going to have to multiply by the conjugate to get that radical out of the denominator. So the conjugate would be 3 minus root 5. I multiply the numerator and the denominator by the same number because I'm just multiplying by 1, which is okay in math. So in the numerator, 4 times 3, I'm distributing. I get 12. 4 times negative root 5 is negative 4 root 5. In the denominator, 3 times 3 is 9. Root 5 times root 5 is 5, and it's a positive times a negative, so it's a negative 5. So our denominator would just be 4. Now at this point, I can actually reduce this because 4 goes into both of these numbers. Over here, 2 went into 10, but it didn't go into 5. So if I'm going to reduce, I have to reduce everything. I have to reduce both of the terms in the binomial. So in this one, 4 goes into 12 3 times, and 4 goes into 4 once. So my final answer would be 3 minus 1 root 5, or just 3 minus root 5. All right, the end. You are now ready for the simplifying radical stretch. Math hard. I'll see you again next time. Bye-bye.